Okay, Ben.
Yeah.
So setting up the sphere, right? Here we go. Now we are able to. Okay, so this is the this is a sphere of volume charge density rho. Okay, so we said we take and we're trying to figure out the electric field at distance d above. So we spoke about symmetry and how all the horizontal components cancel out, because front and back would cancel the piece in the front, piece in the back would cancel the x component of the electric field. A piece on the right of the y-axis, a piece on the left would cancel the y components of the electric field. So the only component that survives is the z component. Clear on that?
Yeah.
Okay, so we take a small patch here, yeah? And this is our separation vector from the patch, the area, the small piece patch, volume element, whatever you want to call it, all the way to the where we are figuring out the electric field at point P. And why don't we call this angle here alpha? So this would be alpha. So the only component that survives is the z component, which is e cosine alpha. Okay? And if we just make a perpendicular line here, so this would be 90 degrees. Okay? Now this here is theta, so this piece here would be r cosine theta. And this piece here would be z minus r cosine theta. Correct? Because the whole thing is z. So z minus r cosine theta. And so now what I could do is relate so what's the separation vector? Well, the separation vector is and this piece here is r sine theta. Okay, so the separation vector would be from the right triangle would be z minus r cosine theta squared plus r sine theta squared square root. Okay. Okay, and of course, if you square this, the square root goes away. So let's square this and then just cancel out the square root. Rho is uniform. I can pull it outside the integral. I know that pi hat, we said, so this is going to be in the z direction. And what's d tau? D tau, it's dlr, dl phi, dl theta, dl phi, right? What's dl in the r? It's dr. What's dl in the theta? It's r d theta. And what's dl in the phi? It's and by the way, phi is, if you project this here, right? Phi is this angle here along the sphere. So dl phi is r sine theta d phi. So this becomes r squared sine theta dr d theta d phi. This is your d tau. And you know, now everything is in terms of r and theta. So just plug everything back in the integral. Oh, and one last thing. Cosine alpha, this guy here, yeah, we can find it from the triangle. So cosine alpha is just, you see how I try to always like plug them in terms of the variables of the you know, variables of integration. So cosine alpha is from the right triangle is z minus r cosine theta over the separation vector. But I've already determined what the separation vector is. So I could just, I could just take this here, square root it, and put it here.
Right.
And now everything goes in the integral. I'm not saying that it's going to be an easy integral, but nonetheless, that's how you could set it up. So E will be 1 over 4 pi epsilon. So this is EZ. We'll just put it in the Z direction. 1 over 4 pi epsilon. Rho, I can pull rho out because it's uniform. Integral of d tau. So this is technically a triple integral. Right? So I have I'm gonna have, so d phi, there's only one phi in the problem, so I could just put d phi here from 0 to 2 pi. Okay. Theta, so here we're gonna have r squared. First we have r squared sine theta dr d theta, and r is going from 0 to big R, the radius of the sphere. Theta is going from 0 to pi, and then this is divided by the separation vector square, which is z minus r cosine theta squared plus r sine theta squared. But then there's cosine alpha, which will be, let me put it here, so this is dr d theta. So cosine alpha is z minus r cosine theta, and so there's separation vector square, and there's another square, another one, so that's square root, and 1 will be 3 over 2. So this is how the integral will look like. Now, of course, this is not a very straightforward integral. It nonetheless could be simplified, because notice here you could, this, if you simplify this a bit, you do get z squared minus 2zr cosine theta plus r squared cosine squared theta, and the second one will get you r squared sine squared theta, and those turn out to be, because r squared cosine squared plus sine squared is 1, so this is just r squared, so the denominator just becomes z squared minus 2zr cosine theta plus r squared. Now notice the beauty. This thing factors. This becomes z minus, oh actually wait, it does not factor. Yeah, because we have that cosine theta thing in the, no, it doesn't factor, so it's going to stay like this. And on top z minus, so this is how the integral will look like. It will take a fairly long time to evaluate this integral, but you do need to complete the square in the denominator. But nonetheless, this is how the setup will look like. Okay, this is how the setup will look like, and so this will only give you a 2 pi, and the theta, there's theta inside of all this, so you do have to work it out little by little. So this is kind of to do the problem from scratch. That's one way to do it, or you could make use of result 2.7, because in 2.7 we did find out that the electric field for a ring, for a shell, was right. Was I think the result was for z greater than r. It looked like a if you're outside the sphere, it looked like a point charge. So it looked like q over 4 pi epsilon z squared, right? It looked like q over 4 pi epsilon z squared in the z direction. This is from problem 2.7, and for z a lot less than r, we worked this problem out. If you remember, I worked this problem out with you. The integral was a little bit tricky, but we did do it. So the electric field turned out to be 0 if you're on the inside of the sphere.
Yeah.
Okay. So what that means is for all.
Be zero with the uniform charge density, though, right?
Yeah. Which means all the shells that are interior to the point contribute as if their charge was at the center, while all the exterior shells contribute nothing.
Right.
And so if that's the case, you know that ER is equal to 1 over 4 pi epsilon Q enclosed, if you like. Q enclosed meaning interior to a point, or the total charge interior to the point that you are considering. So let's just call it Q enclosed over r squared, and this is in the radial direction. Okay? So if you're outside the sphere, all the charge is interior. If you're outside the sphere. So if you are outside, let's use this. Outside the sphere, so the charge is all inside, so E will just be 1 over 4 pi epsilon, the total charge that's on the sphere, and that is just rho times the volume of the sphere, pi r cubed, divided by r squared. And that's in the r direction. So that's if you were outside the sphere. So this would be the result if you're outside the sphere. If you're inside the sphere, yeah? If you're inside the sphere, only a fraction which is interior to the point to which you are considering will count. So in other words, wherever you are, Q enclosed will be, well, on the entire sphere, you have Q over the volume of the entire sphere, or you have rho, basically you have rho, right, times 4/3 pi r cubed, depending on where you are. So this would be your Q, and in that case, E will be 1 over 4 pi epsilon. The Q, this Q, rho times 4/3 pi r cubed, all over r squared. In the radial direction. So this would be the answer for inside the sphere.
Okay.
So, this is sort of a shortcut if you use problem 2.7. But you can always work the problem out from scratch and, just carry out this integral. I mean, it will be somewhat of a pain, but nonetheless, it's doable. Um, and we said that this was in the z direction here. Yeah? Because... yeah. You can go back and recast it in the radial direction, but that's what it is. Questions on this one? So now, do you know how to set it up or no?
I think, so it's basically